It's Cameron again. So some of the real-world applications we chose are readily available online. These are both used generators. The first one is the CAT generator, which runs at about 900 RPM. And if you notice, for our calculations, we calculated for it to be at 1500 RPMs. This puts out 1.23 megawatts of power. And to meet that 1021 megawatt output of the Tracy power plant, we would need about 830 of these, which would put us at an upstart cost of about 150 million, which is not too bad. Again, this CAT generator is a 16-cylinder diesel generator. Another one to compare it to, which is again readily available online and it's also used, is the Wärtsilä generator, which runs a little bit slower, about 720 RPMs. This puts out 6.53 megawatts of power, and to meet that Tracy power plant 1021 megawatt output, we would need about 156, maybe 160 of these, which would put us at a total cost of 300 million to start that power plant. This one puts out more, about 6 times more than the CAT generator because of its bore diameter and stroke, and it has 2 extra cylinders. The CAT generator is a 16-cylinder generator and the Wärtsilä has 18 cylinders. So some of the problems that we run into with diesel are burning fossil fuel. This puts out high CO2 emissions. Another problem with diesel is because of the high pressures maintained inside the cylinders, you need a lot of steel to hold that pressure, which makes starting diesel generators in the cold quite a problem. Another problem for us and the diesel cycle would be the cost of fuel and storing it as well as shipping it.
Hi again, it's Justin Donay, and with me is Joe Michelli, and we will be presenting an analysis of a solar thermal power plant modeled after Solar 2. Concentrated solar power generation is the process of taking a large area of sunlight and focusing it on a single point to power a heat-powered generation cycle, such as a Rankine cycle, which we used for our analysis. In many CSP facilities, there is a heat storage system so that the generator can operate during poor weather or at night. For our analysis, we used a molten salt heat storage system. Economics to consider in concentrated solar power stations are collector cost versus area, optical efficiency of the mirrors, thermal losses in the heat storage system, and the engine efficiency. There are 4 types of concentrated solar power systems, including the dish, tower, trough, and linear Fresnel concentrated solar power systems. For our analysis, we used a solar power tower such as Solar 2. Solar 2, a concentrated solar tower backed by the Department of Energy, produces 10 megawatts at its peak. Heat enters the system through the sun, which releases about 308 watts per meter squared on the Mojave Desert. This heat is reflected by several mirrors or heliostats onto a tower, which heats salt to about 565 degrees Celsius. This hot salt then goes to a hot salt storage tank so that the system can operate during poor weather or at night. This molten salt transfers its heat energy to the Rankine cycle in a boiler. The cold salt is then pumped back into the tower where it is heated by the sun. To break down this process into manageable parts, we first considered the transfer of solar energy to the heliostats and accounted for atmospheric resistivity and the heliostat collection area. Once the heat got to the mirrors, we considered the transfer of the heat to the tower using the reflectance or albedo of the heliostats, the aiming efficiency, and the tower area. We then considered the transfer of heat from the tower to both the surroundings and the salt. Heat is transferred to the surroundings through blackbody radiation, which was proportional to temperature to the 4th power, which is a very large number, but negligible compared to the heat flow through the tower required to meet the Tracy power plant. We then assumed that there was perfect heat conduction through the tower to the salt so that any heat provided to the tower would be perfectly provided to the salt. Heat is then transferred from the hot salt to the boiler in a heat exchanger, which heats the water from 100 degrees Celsius to 777 degrees Celsius, while cooling the salt from 837 degrees Celsius to 285 degrees Celsius. The salt only cools to 285 degrees Celsius because it needs to remain molten at a high temperature.
My name is Joseph Michelli, and I'll be discussing the Rankine cycle of our CSP system. The heat in from the boiler comes from the heat process. At point 3, we have superheated steam, which in turn runs a turbine. This turbine produces work and also saturated steam. That saturated steam is then run through a condenser, where it is turned into saturated liquid. This liquid is pumped and turned into compressed liquid water. That water is then ran through the boiler and is allowed to allow the cycle to run. Here we have a TS diagram for our Rankine cycle. Step 1, we have the isentropic compression in the pump. Then step 2, we have the isobaric heat addition from the boiler. Step 3, we have the isentropic expansion, which is in the turbine. And at step 4, we complete the process with isobaric heat rejection. Here we have the equations used and assumptions made for calculations. As you can see, most of the equations used are from the enthalpy values in the steam tables. The only one that doesn't use that is the pressure volume work from the pump. Below are assumptions and data for the Rankine cycle. We had to do the Rankine cycle calculations first because we knew how much power needed to be produced, but not how much heat needs to be supplied. Our first assumption is our net power of 1,021 megawatts, which is how much power the Tracy power plant produces. Our pressure of water going through pump is 10 megapascals, and pressure of steam after it leaves the turbine is 100 kPa, or right around atmospheric pressure. The data points all come from the steam tables in the back of our thermodynamics book. Most of the data points are enthalpy and entropy values, but we also used the temperature and pressure values of saturated vapor and liquid, and the specific volume of liquid going through our pump. Below we have the calculations for the Rankine cycle. The most important things we found are the amount of heat required, which is Pn. That is 2.7 billion watts, or 2.7 gigawatts. We also found the efficiency of our cycle, which is 37.6%, and also the flow rate, which is 744 kilograms per second, which is a lot, but when you're replacing one of the biggest power plants in northern Nevada, you'd expect to have pretty big numbers.